Hi everyone. So today we are going to talk about the second part of the course, which is on thermodynamics of open system. So for the first part of the course, it was covered by Dr. Ng. So I will be covering thermodynamics of open system, which is the second part, and then the third part will be covered by Dr. Lee. So first of all, I just want to apologize because we have to do a pre-lecture recording, and the reason is because of the coronavirus. So it is good if we minimize face-to-face contact, especially in this situation, so that we can prevent the spread of coronavirus. So the university always wants the best for the students, which is why we do this thing. Okay. So just to introduce myself, I'm Dr. Wen-Da, and this is my email. Okay, this is my email, owenda@usm.mine. Okay. And if you have any question related to this particular topic, you can always email me at my email to set up an appointment. Or if you have any question, you can send it to me. I will reply to you as soon as possible. So this is my contact number, 016-480-8520. You can also WhatsApp me. Okay, WhatsApp me if you have any questions. I will respond to you as soon as possible. Especially since this is a pre-recorded lecture, sometimes when there's no face-to-face interaction, I might speak too fast. Okay, I might not be very clear. You cannot ask during the class because it's a pre-recorded lecture. So you can always WhatsApp me to ask me at what time you're not clear. Maybe this is at the second minute, and you can just WhatsApp me and say, Doctor, you are not clear at 2 minutes. The second minute, please record again. So I will record again. I will send it to you personally. Okay. So I'm at room 121, School of Chemical Sciences. Please feel free to drop by anytime. You can always come to find me. Then, of course, the best thing is make an appointment first because sometimes I may be in a meeting, I may be elsewhere. Okay. So please make an appointment first before you come to find me. Of course, I will also set a time, a consultation time, whereby you can always drop by to ask me any question. Okay, I think this is good because during pre-recorded lecture, we have minimal interaction. So if we have a specific time whereby you can ask questions, then that will be even better, right? At least can you can know and you can understand better. Okay? I can explain anything that you want to know, or you can also give me a passive question. You want the solution, I will solve it and give you the solution. Okay, okay, now let's take a look at what we are going to learn for the coming weeks. Okay, so for this part, we are going to cover different topics. We have three main topics. One is thermodynamics for open system, which we will be covering in week 5 and week 6. Okay, for this week 5, I'm going to give you assignments. Okay, two assignments. First one will be your individual assignment, whereby you will be given a set of questions, about 11 questions from different topics, and you have to solve them and submit to me by 17th of April. Okay, so this is an individual assignment to submit at room 121. Okay, 17th April 2020. Make sure you do that. The second assignment is on group assignment. So group assignment you can submit to me also on the 17th of April. This one you have to form a group of 4 to 5 students to come up with a discussion right up. This one I'll explain a bit further in the subsequent slides. Okay. So at week 7, we are going to cover gas system and real solution. Okay, this is the second part. And you will also be given a quiz 1. Okay. Quiz 1 will cover what you learn in week 5 and week 6. Okay. Given in the remarks here, week 5 and week 6, everything that you learn during week 5 and week 6 will be covered for quiz 1. And then week 8, you have a new topic, phase equilibrium topic. And in week 8, you will have a test 1. Okay? Test 1 will cover everything Dr. Ng taught you, and also part of my lecture, which is the first 2 weeks, okay, week 5 and week 6. So I will cover week 5 and week 6 lecture. So make sure you study for these topics, okay? Thermodynamics for open system. So these are the topics that we'll cover in for test 1. I will also have another one test, which is test 2. Okay, test 2 will be combined with Dr. Lee. We will inform you of the date, and test 2 will cover everything. Okay, everything from my lecture. Okay. So at week 8, I will give you an assignment which needs to be done online. So I will give you more information at week 8. Okay. So hopefully after 2 weeks we don't have to do a pre-recorded lecture anymore. We can go back to our old traditional face-to-face lecture. Some of us may prefer that. Some of us may prefer e-lecture or pre-recorded lecture. Okay, let's see how it goes. Let's see whether the situation improves or not before we decide any further. Okay. Now, just to give you an overview of what is covered. So as I said just now, test 1 will be covering chapter 1 of this part. Okay. Quiz 1 also, chapter 1 of this part. And then we have the chapter 2 and chapter 3, whereby we'll cover in test 2. Okay, test 2 will cover chapter 1, chapter 2, and chapter 3. But more emphasis will be given to chapter 2 and chapter 3, which means that you can expect more questions from chapter 2 and chapter 3 compared to chapter 1, because I have already covered it during test 1. Okay, well, so make sure you study everything for test 2. And for final exam, I will have 2.5 questions. Okay, out of the 7 questions that we have, I will have 2.5 questions. So each question that I have will come from every single part. Okay, that means that we cover everything lah. Okay, we cover C1, C2, C3. Okay, chapter 1, chapter 2, chapter 3 of the course. Okay, now let's move on to group assignment. Group assignment, we have to form a group of 4 to 5 students, and then you have to give me a discussion. So you have to discuss, number 1, application of partial molar quantities. Second is discuss an industrial application of Clausius-Clapeyron equation, which we will learn later. And finally, discuss the industrial application of Raoult's and Henry's law. So you can choose any of these. Okay, you want number 1, number 2, or number 3. Which one you want, you can choose. Only choose one. Okay? Each group only one. Okay, each group one topic. And once you have chosen your topic, you have to write 3-page discussion. Okay, so you will have a total of 4 to 5 members in your group, and make sure that each of the members contribute equally, because at the end of your page discussion, okay, at the end of your discussion on the 3rd page, you have to write the contribution of each members. So make sure you write what's your contribution, what's your friend's contribution, so that I know what you contributed to the paper. So you have to discuss among yourself, maybe form WhatsApp group, who wants to write what and who wants to do literature review and so on, so that you can come up with that discussion. So in terms of evaluation, I will evaluate you based on overall content, okay, which means that every single member will receive the same score. So make sure that everyone contribute. If one of our friend did not contribute enough and you feel like this person will affect your marks, you can, of course, exclude him from the group. Okay? Because what I want is everyone to contribute equally. So if someone is not contributing to the group, he does not deserve a name in the paper. So make sure that you do that. Otherwise, it could affect your marks. So make sure everyone contribute equally and play an active role to ensure that you and submit this discussion. So what I expect is not like you produce a very high-end discussion, very good discussion, or so on. But I want to hear is from your own point of view. Okay, I want to train you guys to do proper research and discussion so that you know what you need to do if you encounter any question, or in the future when you need to do any discussion, what you can do and where you can find your source. Okay, so this discussion also helps you to understand better on the application of physical chemistry to real life. That's why I choose mainly application questions. For example, industrial application, Clausius-Clapeyron equation. Normally what it is used for, where can you find the application of this particular equation? Sometimes people use it for biochemical application, some people use it for this application. So you need to find out, okay, do a literature review, do a literature search to find out what exactly people do or how exactly people apply this equation. Okay, so I'll leave this up to you. Make sure you do a proper job. And I have to remind you again, do not copy paste directly from a source, okay, because I will check. So if I found out that you copy paste directly, this is what we call plagiarism. We don't want any plagiarism. We do not practice any plagiarism. If you copy paste from the online content and I discovered that, so I have no choice but to follow the university policy to give you a 0. Okay, this is quite sad lah to say. Okay, but I believe most of you will not do that. Okay, try not to do that. If really you cannot write, just write based on your own sentence. Okay, you will know that this sentence, okay, this meaning of this sentence is very important to your work. You have to include it in your report. You rephrase everything, okay, and make it like yours. Okay, make it like your sentence, make it original, and then cite that paper. That's the thing that you can do, but never copy paste directly. Okay. The next one, we have the individual assignment, whereby you have to submit it by 17 April. Please don't submit late, because late submission will not be entertained unless with valid reason. If you can submit by maybe earlier, before 17 April, that's very good, right? But if you submit later, after 17 April, I will still accept. Of course, I will not penalize you for late submission, but bear in mind that your marks will be deducted slightly. Okay. Okay, let's start off with our course today. So today we are going to talk about partial molar quantities. And before that, let us just recall back what exactly is open system and closed system. So open system means that you can allow the transfer of energy and matter from the system into the surrounding, right? So you have a system, and outside a system we call it as a surrounding. So if you allow the transfer of matter and energy from the system to the surrounding and the surrounding to the system, then we call this as the open system. Whereas closed system means that you can only transfer energy. Okay? Matter will remain inside the system, and you cannot transfer matter inside or outside from the system, which means that you only allow the transfer of energy from the system to the surrounding, or from the surrounding to the system. There's another one system which is what we call as isolated system. Isolated system means that we allow no transfer of anything, okay? Which means you cannot have energy transfer, you cannot have matter transfer in an isolated system. Okay. So another two things that I want you to know is the extensive variable and intensive variable. What are the difference? Okay. So extensive variable means that that particular variable depends on the composition of the system. For example, you have, let's say, volume. Volume depends on the composition of the system. You have Gibbs free energy, you have enthalpy, and so on. Okay. So intensive variable means that it does not depend on the composition of the system. One example is density. Density, you don't depend on the composition of the system. And pressure does not depend on the composition of the system. Temperature also. So these are some of the examples of intensive variable. So when we talk about partial molar properties, we are actually discussing on how extensive property of a particular solution or mixture can vary with regards to the molar composition at constant temperature and pressure, which means that we want to know, or we want to quantify how extensive properties can change. For example, volume, how volume can change with different molar composition. And usually we use these partial molar properties to discuss individual components in the system, especially in the mixture. For example, in the mixture, if you have two different types of compound, for example, compound A and compound B, when we talk about partial molar properties, we are actually talking about either partial molar properties for compound A or partial molar properties for compound B. Okay, so in an open system, of course, this is the system that we are going to discuss throughout this lecture. Open system, which means that there's a transfer of matter and energy from the surrounding into the system and from the system to the surrounding. Okay. So there will be some changes in terms of the composition. Okay. So composition means that the amount of matter present in the system. So different composition will lead to different changes in the extensive variable. So extensive variables such as volume, internal energy, Gibbs free energy, entropy, enthalpy, they all depends on the composition, which we will see later. Okay. So all these changes in the system, okay, the changes in the composition of the system will influence the extensive variable. Okay. Let's take a look at an example if we have one component system. Okay. If we have one component system, then it's very simple. Okay. So let's say we want to look at a one component system for internal energy. If we have only A, if we add in, let's say we start off with 1 mole. Okay. 1 mole internal energy is 2, for example. So if we add in another 1 mole of A, which means the mole of A becomes 2, right? So the internal energy is proportional to the number of moles, which means that we have 2 internal energy when we have 1 mole of A. So when we have 2 mole of A, the internal energy is 4. Okay. So this is pretty straightforward, which means that the internal energy and number of moles of A is proportional. They are linearly proportional to each other. But the problem arises when you have two components. Okay. So if you have A, it interacts with A, then that they have similar interactions, which means that they're almost the same, right? They don't really cause any effect in terms of the intermolecular surroundings. Okay. But of course, if you have different components, you have A and you have B with different properties and different characteristics, then there's a percentage chance whereby A and B can have certain interactions which will affect the extensive variable. So let's take a look at the volume. Okay, this one we will discuss in more details later. This is just an example to show you how the extensive variable changes with respect to different mole fractions of ethanol. So look at this ethanol. Okay, this is the partial molar volume for ethanol. Okay, look at this side. This side. Okay. So for ethanol, you look at this axis. For water, you look at the other axis. So you can see that it's not a linear graph. Okay. When you add in, let's say, okay, this is the total volume. Okay, this graph. You add in water and ethanol in a beaker. The volume, the total volume of that particular mixture will depend on the composition of ethanol that you have. let's say if you have, okay, this, you look at this total volume. If you have a composition of X, let's call this X as ethanol. Okay, this is ethanol. If you have 0.5, right? So the total volume will be this one. This is the total volume, the peak over here. Okay. Whereas if you have a different composition, let's say 0.9, and the total volume will be different, right? It's way lower than when you have composition of 0.5. Okay. So this means that different composition in that particular system will affect the amount of extensive variable. Okay. Okay, let's take a look at an example of a two-component system. Let's look at the volume of a two-component system. Let's say if you add in 50 cubic meter of water with 50 cubic meter of ethanol, okay, at a constant temperature and pressure. Okay, when you add into, what you expect the volume to be is 100 cubic meter, right? Because 50 plus 50, you expect to get 100, right? But however, experimentally, when we add in 50 cubic meter of water to 50 cubic meter of ethanol, you only get 96, okay? 96 cubic meter, which means you have 4 cubic meter short, right? So this is because when you add in water and ethanol, water and ethanol, they have different characteristics. Their molecules have different characteristics. So there could be certain intermolecular interactions between ethanol and water that makes the volume decrease. Okay? So the intermolecular interactions plays a very critical role. So when you have a stronger intermolecular interactions, which means the molecule pulls the surrounding molecules closer to itself, which means you have a stronger interactions. That means you will have a lower volume, right? If you have similar interactions, let's say you only add in 50 cubic meter water to 50 cubic meter of water. What happens is that you have similar interactions. That means you could expect the total volume of adding 50 plus 50, it will give you 100. But when you have different, then it will start to give you different results. Okay, like water and ethanol, 50 plus 50, you get 96. So for ideal solution is when you add in two different things, okay, two different components, and you get, let's say 50 plus 50, 100, you get the sum of the two volume. This is what we call the ideal solution, whereby the interactions between the two components are almost the same, very similar. That's why you have almost perfect summation of the two volume. But if you have non-ideal solution, okay, which means that one component and you add in another component, you have different intermolecular interaction. Okay, perhaps when you add in both, the intermolecular attraction becomes stronger, then your volume will decrease. When it becomes weaker, then your volume will increase. So this is what we call a non-ideal solution. Okay. So different molecules, they have different interaction strength. So this is a very general statement. So unless you have two molecules behaving similarly, which means that they have the same intermolecular interaction, then you can say that both molecules will give you the exact summation. 50 plus 50, you will get 100. If not, then you will not get the same. So because of this, there's a variation with the composition. So different composition, you will get different results, okay? Different interactions. And when you have different interactions, you get different volume. So not only volume, Okay. Other extensive variables such as internal energy, okay, or U, gives free energy, enthalpy, they are all affected by this phenomenon. So to determine what are the extensive properties at different composition, we can use the slope. Okay. So when we use the slope, okay, the slope is actually known as the partial molar extensive properties. Let's say if you use it to determine internal energy, then we call it partial molar internal energy. If we use it to determine volume, then we call it partial molar volume. Okay, so the definition of partial molar internal energy or any partial molar external properties is given by this equation. Okay. So you have the partial, for example, the partial molar internal energy is equals to the del U final over del NB, okay, at constant temperature, pressure, and your number of mole of A. Okay, so remember this interactions between the molecules is important because they will determine, okay, whether you have, let's say for volume, you have higher volume when you mix the two mixture A and B, or you have lower volume when you mix the two mixture. Okay, so only the case when they have the same interaction, okay, A and B, they have the same interaction, then you can call it as ideal solution, which means 1 plus 1 equals 2. You have the same, almost the same summation of the two external properties. Okay, now let's take a look at how we can actually derive the partial molar quantities for a system, which means that we want to mathematically describe how we can determine the partial molar quantities. So let's look at this system consisting of many components. Let's say from N1, N2, N3 up to Nj, which means you have many components. Okay, so let's write it as a function. So x, which means x is the extensive variable. Okay, let's take x as the extensive variable. X can be volume, it can be Gibbs free energy, it can be anything. So this x is a function of pressure, temperature, and all the components in the system, N1, N2, N3 up to Nj. So this function, if you want to differentiate it, right, you can write it like this. So dx is the differentiation of x is equals to del x over, because you can see that you have P, T, N1, N2, N3 up to Nj. So you start off with the first one, del x over del P, okay, del x over del P, dP at constant temperature and N, okay, all the N here has to be constant, okay, all the N here has to be constant, okay, plus del x over del P, the second one, okay, at constant pressure and all the N dt. So you notice that this the first part del P and dP the same, del T and del T dt the same. Okay. After that plus del x over del n. Del n is the first component. Okay. Constant temperature, pressure, and all the components except n1, d n1. Then plus del x over del n2, temperature constant, pressure constant, all the n constant except n2, dn2, and so on. So you do this for all the component in the system. Okay, so this is how we differentiate x. So I repeat again, if you want to write the differentiation of dx, right? So you write dx, and then equals to, you differentiate one by one, the variable one by one. then you will get to write the whole full equation over here. Okay, so after that you can simplify it to become this equation. Okay, you can simplify it like this: dx equals to del x over del p at constant p and order n dp plus del x over del t at constant p and order components dt plus the sum of del x over del n at constant t, p, and selected components dn. Okay, so x, repeat again, this is the extensive variable, which means that x can be volume, can be Gibbs free energy, it can be entropy, and so on. Okay, so this is how we look at the term del x del p at constant t at nk dp. It means change in x caused by change in p when p and n are constant. Okay, same thing for del x over del t, change in x due to the change in p. Okay, when p and n, they are constant. Okay, and the same thing for del x over del n, which means change in x by the change in number of moles for I. Okay, when p, p, and other components are constant. Okay, so we can actually define the partial molar quantity as this equation. So this x I, okay, with the bar on the top of it, this is how we write the partial molar quantity for component I. Okay, so I here stands for component I is equals to del x over del n I. Okay, and I is the number of moles of component I. Okay, at constant temperature, pressure, and other component in the system. So we write it like this. Okay, for the partial molar quantity. So we include this equation into the equation that we derived previously, then we will get this. So you can see this one. What we did was we only substitute del x over del n dn with the x. So this one. Okay, this part. So everything is the same except we substitute this part, this one, and this one. Okay. So when we substitute it and we want to simplify it, we can simplify it to become like this. Dx equals to del x over del p, constant p, constant n, dp plus del x over del t, constant p, constant n, dt plus the sum of the partial molar quantity of all the components in the system. So if we look at an example whereby x is actually your g, g is your Gibbs free energy. So Gibbs free energy is a function of pressure, temperature, N1, N2, N3 up to N-day. So this one we can write it. Okay. We have discussed about this just now. So when we want to convert this G into its differentiation, so we can directly write this easily, right? We have discussed about this in the previous slides. dg equals to del g over del p, constant p, constant n, dt plus del g over del t, constant p, constant n, dt plus the sum of del g over del n, whereby n is the component. Okay, if you have two components, you have n1 and n2. If you have three components, n1, n2, n3. Okay, so if we want to write the partial molar free energy for the component I, okay, if we want to write the Gibbs free energy, you can write it like this: G I with a bar on the top of the G. This is how we write the partial molar Gibbs free energy. If it's for volume, then we just write V for component I. So this is for volume. Okay. So this G has some significance because this is also your chemical potential. The chemical potential is defined as del G over del N at constant T, P, and other components. Okay. So like just now what you say, we can simplify this equation. We can simplify it to become like this. Okay. Okay. So this is what we have simplified the equation to become. Okay. So each of this term has its own meaning in these two terms with its own meaning, which means that del G del P is basically change in G caused by the change in pressure and caused by change in pressure when temperature and composition they are constant. Okay, it's all written in the mathematical formula. It's very easy to read. Del G over del T, which means change in G at different temperature at constant T and N. Okay, which means N is the component. Okay. So we compare this equation, okay, with the fundamental equation of Gibbs free energy. Okay, we can compare it. Compare dg equals to v dp minus s dt. Okay, if we compare these two equations, what you can see is that they are almost similar, except that for the equation that we derive, you have additional term. Right. This additional term is because we are dealing with an open system. Whereas the fundamental equation, okay, this fundamental equation, I believe Dr. Ng has already covered this equation. This equation is for closed system. Okay. So if we compare this, the one that we derive and the closed system, what you will see is that there are some similarities. This part, del G over del P dP is similar to the VdP, whereas this part, del G over del T dt is similar to the S negative S dt. So you know that thermodynamics, they are all related to each other. So we can actually relate del G del P at constant T and all the components dP, okay, we can relate it with the volume, and del G del T constant pressure and Nk is your negative S. Okay. So like I said just now, if you compare it with the closed system, you can get to simplify the equation further, right? So this one, del G del P Tn V and del G del T P, constant P and constant N is negative S. Okay. So the only thing that is different if you compare the closed system and the open system is in terms of the composition, right? Open system, you have transfer of matter in and out from the surrounding to the system and then from the systems to the surrounding, which is why you have to have an additional term. So this is the additional term to cater for the open system. So if we want to derive other different equations, let's say you want to look at the enthalpy. So G is equals to H minus Ts. This is a fundamental equation that you learn in your thermodynamics first part, right? So from your dg equation, right, you take this G, you break it up into H minus Ts. Okay. So dH minus Ts is equals to VdP minus SdT plus your partial molar properties, right? Then from here you can further split dH minus Ts becomes dH minus TdS minus SdT. So this split is because you have dH minus, okay, Ts, right? So it's basically equals to dH minus d ds, right, which is equals to dh minus tds. Okay, you have to differentiate one by one. dds is equals to t, constant t, differentiate ds, plus constant s, differentiate dt. Okay, this is how we split it. dh minus tds plus sdt. Okay, so taking into account the negative sign over here, then your dh minus tds minus sdt, it becomes this, and then after that equals to vdp minus sdt plus your partial molar property. So in the end, after you bring this negative sdt and tds over to the other side, you end up with dh equals to vdp plus tds plus your delta gives free energy, okay, or chemical potential, dni. Okay. So if you want to relate to internal energy and Helmholtz energy, you can do that also. So if you want to relate it to that, okay, first you have to split the equation further. H is equals to U plus PV, right? So your dH, you can change it to D U plus PV. Okay. So using the same rule just now, du plus dPV, which is equals to your du plus constant P dV plus constant V dP. So when you have a differentiation of two different things, okay, the multiplication of two different things, okay, like dPV, you have to split it into PdV plus VdP. Okay, you have to split it into two. So once you split it, then the whole equation becomes like this: du plus PdV plus VdP. You will end up getting equals to VdP plus TTS plus sigma mu I dN. Okay. So from here you can bring PDV and VDP to the other side. You end up getting your equation for du. So for Helmholtz energy, if you want to do this for Helmholtz energy, first you have A equals to minus Ts plus U, right? Or A equals to U minus Ts. Okay. So from the previous equation du, you take this U, you replace it with A plus Ts. So U is equals to A plus Ts, right? So from here, you do the same thing, dA plus dTs, which is equals to dA plus EDS plus SDT, equals to negative PdV plus TDS plus your partial molar properties. And then you will end up getting dA equation. So let's look at an example. Let's say you have a system consisting of two different components. Okay, let's try to derive something. Okay, let's say volume. I want to look at volume, and you have two components, which means that you have to have constant P, constant T, and then you have two components N1, N2. So if we have a problem like this, we want to derive the partial molar volume. So what we can do is very simple. First, we have to write a differentiation equation. dV is equals to del V, okay, over, you can see here you have 4 variables, 1, 2, 3, 4. So you have to have first variable del p at constant temperature, N1 and N2. B, B. This is the first term. So if you look at this one, you have 1, 2, 3, 4. That means you must have 4 terms. Plus del V over del the second term. This is the temperature term. Constant pressure N1 N2. Right. D plus del V del N1 constant temperature, constant pressure, and constant N2, D N2, and final term is del V over del N2 at constant temperature, pressure, and N1. So this is how we write the differentiation for volume, right? Partial molar properties of volume. Okay, and we have several variables: pressure, temperature, N1 and N2. So this is how we write it. Okay. So if I give you a question, ask you to derive something, okay, for 3-component system, so you have to add in another one term, right? If it's 3-component, you have to add in N3, and then you have to add another term with N3 inside. Okay? So now to simplify this, right? To simplify this further, you have del V over del P, right? You have T N1 N2 dP plus del V over del T dt P, okay, N1 and N2 plus with the sum of del V over del N I dNi constant pressure, temperature, and N not equals to I. Okay, so this is how we write the overall things. So hope you get how you can write this. If you have any problem, please feel free to get back to me. And yeah, we will end today's first lecture here. Thank you.